In 1915, Einstein stood in front of the Prussian Academy of Sciences and unveiled general relativity, a new way of thinking about gravity, not as a force, but as a curvature of space-time. For many, this was still a philosophy rather than real physics. Equations elegant on paper, yes, but what did they describe? What did they predict? Just 2 months later, an answer arrived from Karl Schwarzschild, a German physicist serving in the First World War, who lay sick in a field hospital on the Russian front. In between calculating artillery trajectories, he somehow found the clarity to solve Einstein's equation for the simplest possible case, a spherical, non-rotating and uncharged mass. Karl then wrote a letter to Albert Einstein. "Honored Mr. Einstein, in order to be able to verify your gravitational theory, I have brought myself nearer to your work on the perihelion of Mercury, and occupied myself with the problem solved with the first approximation. Thereby, I found myself in a state of great confusion, but I was able to find the following results. It is an entirely wonderful thing, that from one so abstract an idea comes out such a conclusive clarification of the Mercury anomaly. As you see, the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take a walk in a land of your ideas." His letter to Einstein contained the first exact solution to general relativity, now called the Schwarzschild metric. Einstein himself was surprised. He hadn't expected a closed-form solution to be possible. But Schwarzschild never lived to see the implications of his work. He died in 1916 from a rare autoimmune disease, just months after sending that letter. The first black hole solution came not from a professor in an office, but from a soldier scribbling away dying in a war. The Schwarzschild solution became the foundation. It told us what spacetime looks like, how stuff falls and orbits around an idealized mass with nothing else. No rotation, no charge. But physicists knew immediately, real astrophysical bodies are rarely so simple. What if they spin? What if they carry electric charge? Would Einstein's theory still give an exact solution, or would the equations become insolvable? That is where the Reissner-Nordström solution enters the story. To understand the next leap, you have to recall that general relativity doesn't live in isolation. At the same time, Einstein was rewriting gravity. Maxwell's equations has already given physics a unified theory of electricity and magnetism. So the natural question was, how do these two great theories interact? What does spacetime look like around a mass that is electrically charged? In 1916, Hans Reissner, an engineer and physicist in Berlin, published a solution. Independently in 1918, Gunnar Nordström in Finland derived the same result with a slightly different formulation. Today, their names are forever tied together as the Reissner-Nordström metric. So, what is it? It is the general relativistic description of spacetime around a spherical, non-rotating, electrically charged mass. In other words, take a Schwarzschild black hole and give it electric charge, and you get a Reissner-Nordström. This seems like a small modification, but the physics it reveals is extraordinary. Because adding charge introduces a second source of curvature, gravity pulls inwards, but electric charge pushes outward. A charged black hole has a constant tug-of-war between attraction and repulsion, and the geometry of spacetime reflects that. In Schwarzschild, you get a single event horizon, the spherical surface from which nothing, not even light, can escape. In Reissner-Nordström, you suddenly have two. The outer event horizon looks similar to a Schwarzschild, but inside of it there is another, an inner horizon called the Cauchy horizon. Beyond it, the mathematics become unstable, sensitive to the smallest perturbation. This layering of horizons changes the causal structure of spacetime itself. And there is more. If the charge is too high, the horizons disappear altogether, leaving what's called a naked singularity, a point of infinite curvature visible to the outside universe. That possibility is deeply unsettling, because general relativity relies on cosmic censorship. The idea that singularities are always hidden behind horizons, never exposed. A naked singularity means predictability breaks down. Physics itself stopped making sense. Suddenly, what seems like a minor tweak to Schwarzschild had uncovered the boundaries of what relativity could allow. Let's pause and build some intuition for what charges does here. In Newtonian gravity, you might imagine stacking two forces, gravitational attraction and Coulomb repulsion. But in relativity, these aren't separate. Both gravity and electromagnetism shape spacetime itself. The Reissner-Nordström metric encodes the combined curvature. And when you solve Einstein's field equations with Maxwell's energy-momentum tensor, this geometry falls out naturally. Physically, it means light rays, particles, and even the fabric of time follows geodesics, distorted not only by mass, but also by charge. A particle falling into a charged black hole doesn't simply accelerate inward, but it feels an additional resistance, if it had the same sign of charge, or an electric pull if opposite. That subtly shows up in the structure of horizons. The outer horizon is the familiar boundary of no return, but the inner horizon acts like a mirror of sorts. The equation suggests that if you pass through it, spacetime can continue, even extend to other regions that look like new universes. Penrose diagrams of the Reissner-Nordström solutions show an infinite ladder of repeating universes connected through these inner horizons. This sounds like science fiction, but it comes straight out of the maths. However, physics is less forgiving. Real black holes are not perfectly isolated. That inner horizon is highly unstable. When any disturbance falls into the black hole, a photon, a ripple of gravitational energy, even the faint glow of the universe itself. Small perturbations, say, in falling radiation pulled inward, it gets exponentially blue-shifted. Its energy density grows larger and larger. This is known as mass inflation. So, instead of a smooth passage, the inner horizon collapses into a true singularity. You'd get instantaneously ripped into shreds. So, the dream of slipping through a black hole to a separate universe doesn't survive real physics. The equations offered hope, but nature slammed the door shut. There is a special case worth pausing on. The Extremal Reissner-Nordström black hole. If you keep increasing the charge of a black hole while holding mass constant, the two horizons, outer and inner, get closer. At a critical ratio of the charge to mass, they merge. That is the extremal limit. In this state, the surface gravity at the horizons becomes zero, which means that the black hole no longer radiates Hawking radiation in the usual way. Classically, the Reissner-Nordström black hole looks perfectly black. Once it forms, the outer horizon stands out like a perfect shield, hiding everything inside forever. But in the 1970s, Stephen Hawking asked, what happens if we don't ignore quantum mechanics at the horizon? His calculation revealed something shocking. Horizons aren't completely silent. They emit a faint glow, as if the vacuum itself were leaking energy. This is Hawking radiation. It comes from quantum fluctuations. You see, pairs of virtual particles constantly pop in and out of existence. Normally, they annihilate instantaneously. But here, near the horizon, one can fall and the other escapes. To the outside world, it looks like the black hole is radiating. And because energy must be conserved, the black hole slowly loses mass. But to a Reissner-Nordström black hole, Hawking radiation means more than just shrinking mass. It tends to discharge the black hole too, because charged particles are preferentially emitted. That means the elegant double horizon solution we drew on paper can't last forever in reality. Why does this matter? Because extremal black holes play a crucial role in theoretical physics. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes have an entropy proportional to the area of their horizon. For ordinary black holes, this was a puzzle. Where did this entropy come from? But in string theory and supersymmetric theories, extremal black holes allowed physicists to count the underlying quantum states directly. Strominger and Waffa in 1996 famously derived the Bekenstein-Hawking entropy from the first principles using extremal black holes. In other words, the Reissner-Nordström family sits right at the intersection of relativity, quantum theory, and string theory. It is not just a curiosity of charged objects, it is a laboratory of testing the very foundation of physics. Now comes the natural question. Do charged black holes exist in nature? After all, most astrophysical objects are nearly electrically neutral. Any excess charge would quickly be cancelled by surrounding plasma. So you might think, no, this is a mathematical toy irrelevant to the universe. But that misses the deeper point. The Reissner-Nordström solution shows us how general relativity integrates with electromagnetism. It lays bare what the theory permits even if the cosmos rarely realizes it. And those insights spill into real astrophysics. For example, charged black hole solutions are used as testbeds for numerical relativity to study stability, cosmic censorship, and horizon thermodynamics. They also model the behavior of black holes in higher dimensional spacetimes, which crop up in string theory. And there is another reason to care. Extremal charged black holes appear as exact traceable cases where quantum gravity can be understood. Even if nature never assembles a macroscopic charged black hole, the equations tell us something about the architecture of spacetime itself. They reveal the edges of what relativity could handle before breaking down. And those edges are exactly where new physics tends to emerge. The Reissner-Nordström black hole sits in a fascinating place. It is both a historical artifact of the early days of relativity, worked out within just a few years of Einstein's theory, and a modern tool at the frontier of theoretical physics. It tells us that adding one ingredient, electric charge, reshapes the entire landscape. Multiple horizons, possible naked singularities, extremal states where entropy and quantum gravity connect. It also forces us to confront questions that remain open. Does cosmic censorship truly forbid naked singularities? Or can a Reissner-Nordström expose them under some conditions? Do inner horizons really evaporate under perturbations? Or could there be some exotic state of matter that stabilizes them? And why do extremal black holes fit so cleanly with string theory microstates? And what does that say about the true microscopic nature of spacetime? The Reissner-Nordström black hole is not just an exotic geometry in a textbook. It is a reminder that the universe hides structure deeper than our intuition suggests. And sometimes, the path to the structure begins not with observations in the sky, but with a few pages of equations, scribbled in the most unlikely of places. If the strange, sometimes paradoxical lives of black holes captivate you, and you want to witness more of the universe's secrets revealed through careful observations and deep reasoning, subscribe and join our journey. Each video is a step further into the cosmos, exploring the hidden mechanisms shaping reality itself.